key socioeconomic indicator that reflects the health of a nation's economy. The project is aimed to understand the trends and patterns in unemployment across Malaysian states by using least square approximation techniques. The dataset will be modeled with linear, polynomial, and exponential functions. Each model will be evaluated using the sum of square errors to identify the best fit. The best fitting model will be used to predict future unemployment rates, offering insight into potential trends and challenges. Next is objective. First objective is to identify the best fitting model to predict the annual employed person in Malaysia. Second is to evaluate the sum of errors of each model function to identify the most accurate representation of the data. Third is to offer actionable and recommendations for leveraging the best model to understanding and addressing unemployment issues in Malaysia. Data and data source. The data for this analysis was sourced from the official Department of Statistics Malaysia that show the number of unemployed person yearly from 2000 until 2023 in Malaysia. From the table, we can see the independent variable, which is X, is year, and the dependent variable, which is Y, is the number of unemployed person in Malaysia, and the data, we take 24 data.
Next, I will present about least square linear function. So the least square linear function is a mathematical method that we use in statistics and data analysis to find the best fitting straight line for a set of data points. This method minimizes the sum of the square difference, which is errors between the observed data and the predicted values from the linear function. So what are the steps that we have to do to fit this least square linear function? So, start fitting a line. The first step is write the linear function to be fitted, which is fx equal to a naught plus a1x. Second, determine the respective values. So, I have used the Excel to determine the respective values. So, x is represent year, which is start from year 2000 until year 2023. So, the total number of data we have is 24. Y is the value of unemployment person. So for fitting this function, we have to find x squared and xy. So we have here summation x, summation x squared, summation y, and summation xy. Next, we have to write the normal equations in the metric form 2 times 2. So here here is the normal equation in metric form 2 times 2, which is n summation x summation x square a naught a1 summation y and summation xy. So from the data we have gathered, we have number of round is 24, summation x equal to 300, summation x square equal to 10,000 and 60 40 200.1, summation y 4,900, and summation xy 878.7. So we substitute all the value into these normal equations. And then after we substitute all the value into the normal equation, we solve for a0 and a1. So for our group, I have used grammar rules to solve the a0 and a1. So for the A, we have 165,810.4, A0 7482680, and A1 2103088.8. So to find A0, the formula is large A0 divides by A. So we have 45.2371. So next for A1 is A1 divided by A. So we have 12.7144. Therefore, the least square line is fx equal to 45.2371 plus 12.7144x. Finally, we have to plot the least square line using Excel. So I using Excel to plot the least square. So this is the final graph that we get. So this graph illustrates an overall upward trend in unemployment represented by the equation we get earlier, which is fx equal to 45.2371 plus 12.1744x, indicating a steady increase over time.
So this is the data for the least square polynomial function. From the table, we can see we take 24 iteration, and the table show the data of x, y, x square, x power of 3 until x power of 10. And then we calculate the sum of x, y, x square, x power of 3 until x power of 10 using the Excel. This is the continued table from the previous slide. So the table show the xy, x square y, x power of 3y, x power of 4y, and x power of 5y. So using the Excel also, we calculate the sum of xy, sum of x square y, x power of 3y, x power of 4y, and sum of x power of 5y. Next, we continue to the step. So first step, we need to determine the degree m of the polynomial and write the general expression of the polynomial. So we take the degree of 5, and the general expression of the polynomial is f x equal to a9 plus a1x plus a2x power of 2 plus a3x power of 3 plus a4x power of 4 plus a5x power of 5. So the next step is we need to write the normal equation in metric form 6 by 6. So this is the normal equation in metric form 6 by 6. Let's go to the next step is calculate the coefficient needed in the matrix. So n, which is the total of data points. So our n is 24. Next, we insert the value from Excel for all the elements in the matrix. So this is the value that I got for Excel, and I put to the matrix. And next, we can solve for the coefficient a9, a1, a2, a3, a4, and a5. Next, we're going to the next step is by solving the matrix. The value for a0, a1, a2, a3, a4, and a5 are a9 equal to 316.48, a1 equal to negative 30.869, a2 equal to 10.344, a3 equal to negative 1.5289, a4 equal to 0.0866, and last one a5 equal to negative 0.0016. So we go to last step is fit the values into the equations. So the least square polynomial function is f x equal to 360.48 minus 13.869 x plus 10.344 x square minus 1.5289 x power of 3 plus 0.0866 x power of 4 minus 0.0016 x power of 5. The best fit curve line of the polynomial function equation of order 5. So on the graph we can see the number of unemployed persons in Malaysia per year, and on the graph also we can see the least square polynomial function equation. On the graph also we can see the point for the data and the curve line based on the data.
Now we will look at the alternative function, which is we use exponential function. What is alternative function? Alternative function is a mathematical function that serves as substitute or a different representation of another function or model, often used to simplify or approximate a more complex system. The purpose of an alternative function is typically to provide a more convenient or efficient way of solving problems or analyzing data, especially when the original function is difficult to work with or does not have a simple closed form. It may involve a different form such as polynomial, trigonometric, or exponential functions to represent a particular relationship between variables. For this report, we use exponential function. Why? Because it is the most suitable way to model unemployment rates, and it can effectively capture the rapid changes in employment levels, especially during periods of economic growth or recession. Unemployment rates tend to change continuously over time, with growth or decline occurring at a rate proportional to the current rate of unemployment. The exponential function can model the dynamic by reflecting how the unemployment rate may grow or decrease more quickly in certain economic situations, providing a realistic approximation of trends over time. Next, we will look at the step how to calculate the exponential function. First, we must identify the expected function y. The formula is y equal to alpha exponent beta x. And for the step 2, is to identify the unknown, which are alpha and beta. For the step 3, we have to linearize the relationship of the independent and the dependent variables. First, we write down the function y, which is y equal to alpha exponent beta x. Now, we will put ln at the both sides. So we will get ln y equal to ln alpha exponent beta x. Now we will separate the equation. So we will get ln y equal to ln alpha plus ln exponent beta x. Next, we will take the beta x to the point. So we will get ln y equal to ln a plus bx ln e. As we know, ln e equal to 1. Therefore, we will get ln y equal to ln alpha plus beta x. Step 4, which is transform the data. As we know, the general expression for the function y is a0 plus a1 multiplied with x. By comparing the equation after linearization and general expression, we can get y equal to ln y. Meanwhile, x equal to x and a0 equal to ln a. Lastly, a1 equal to beta. For the step 5, we must identify the normal equation. This is the formula for the normal equations. For the step 6, we must to determine the respective values. We use SL to get the respective values, and we will get the summation of x equal to 300. Meanwhile, for x squared, we get 4900. For summation of y, we get 145.629. And lastly, for x multiple with y, we get the summation is 1855.026. Next, we will go to the step 7, which is to substitute the respective values in the normal equation. We substitute the respective value in the matrix. So we can get in the matrix 24, 300, 100, 4900. At the next, we got a0 a1 equal to 145.629 and 1855.026. Then we will go to step 8, is to solve for the coefficients. How we get the coefficients? Now we calculate it by using calculator. After that, we will get a0 equal to 5.6911, and for the a1 we got 0.0301. For step 9, we will solve for the model unknowns. At the previous, we got a0 equal to ln a, and we already have the answer for a0, so we will substitute the a0, which is 5.6911 equal to ln alpha. Then we will put the exponent at the both sides. So we got exponent ln a equal to exponent 5.6911. As we know, exponent ln we can get 1. Therefore, we will get alpha equal to exponent 5.6911. Then we will solve the exponent 5.6911. So the answer for alpha equal to 296.22. Also, at the previous, we got the formula for a1 equal to b. And we already have the answer for beta, which is 0.301. For the last step, we will write the model obtained for the data. So the original function y equal to alpha exponent beta x. Now, we will substitute alpha and beta. Then you will get the formula for function y equal to 299.22 exponent 0.0301 x. This graph shows the best fit curve line for exponential function for number of unemployed persons in Malaysia per year. The graph shows the number of unemployed persons in Malaysia over the years modeled by the exponential function, which is y equal to 296.2 exponent 0.0301 multiplied with x. It highlights a general upward trend in unemployment with a positive growth rate, while the model aligns with the overall trend. Some year variations, particularly in later years, indicate it may not fully capture fluctuations or anomalies in the data.
Next is sum of square error as SSE. So the first one, SSE for least square function, I have used Excel to find the SSE. So for SSE, we have X, which is represent for year. Observe Y is Y, which is the value of unemployment person. Next, Next is calculated Y. So for calculated Y, how we are going to find this calculated Y is we substitute all the value of X into the equation we get earlier, which is we substitute the value of X into this equation, which is 45.2371 plus 12.7144X. So for X in the equation, we substitute with the all value for X, which is start from 1 until 24. And then for area square, formula for area square is calculated Y minus observed Y square. So for each data of X, we have calculated the area square, and we finally get the summation of area square is 1,433,000 and 956.14.415. So this sum of square error indicates that the linear model fx does not perfectly fit the observed data with significant deviations, particularly around data points like x equal to 21 and x equal to 22, where at this point where sharp increases occur.
Next is sum square error for polynomial function. So that is the table of the SSE. And the equation for the y new is negative 0.0016 as power of 5 plus 0.0866 as power of 4 minus 1.5289 as power of 3 plus 10.344 as square minus 13.869 as plus 316.48. So SSE is equal to sum of E squared. So from the table and outside, we got the SSE is 159,424.374.1. The sum of square errors SSE for the polynomial function is 159,424.37, indicates that the polynomial function provides a general approximation of the unemployment data, but the noticeable deviation between predicted and actual values. This suggests that while the model captures the overall trends, it may not fit the data perfectly due to the complex fluctuation.
Now, we will look at the sum of square error for exponential function. First, we must identify x and y. Now, we will need to find y prime. Y prime, we got from the formula from function y after we substitute alpha and beta. So we get the formula for y prime equal to 296.2 exponent 0.0301 multiple with x. After we calculate y prime, we must to find error, which is by subtract y prime minus y. And after we got the error, we must to square error because we want to get the error square. So the sum of square error SSE for the exponential function is calculated as 51,488.9, representing the total square differences between the observed value y and predicted values y prime. This value indicates how well the exponential model fits the data, with smaller SSE values implying better accuracy. Next, we will look at the prediction. For the prediction, based on the calculated sum of square errors, or we call it SSE, we can conclude that the exponential function is the best fit for predicting future trends, as it has the smallest error. First, we will write down the exponential function, which is y equal to alpha exponent beta x. Now, we will get the best fit function for predicting future data is y equal to 299.22 exponent 0.0301 multiple with x. Now, we want to predict future data, so we want to know the 5 years ahead. Therefore, we will must to plus 24 data plus 5, and we will get the x equal to 29. Now, we will substitute this x to the exponential function to predict the future data. So, we will get 709.06. Therefore, it is 710. In conclusion, for the next 5 years, when x equal to 29, it is predicted that there will be a 710 unemployment rate in Malaysia. Then, predictive capabilities. For the accuracy, exponential function has the lowest SSE, which is 41,488.9. Lower SSE implies a closer fit to the observed data, reducing discrepancies between predicted and actual data. And it also captures the general upward trend in unemployment effectively. For the simplicity, the exponential function involves only two parameters, which is alpha, initial unemployment level, and beta, growth rate. Therefore, it avoids overfitting risk associated with higher order polynomial models. And it also reduces computational complexity compared to models with numerous coefficients. For the interpretability, the exponential function widely used for phenomena exhibiting proportional growth or decay. Example, unemployment trends. And the parameters alpha and beta have clear real-world meanings. Therefore, it aligns well with economic trends where unemployment rates grow proportionally under specific conditions. However, there is limitation for exponential function, which is it struggles to account for significant anomalies or abrupt changes in unemployment rates, as these are typically non-exponential in nature. And it also less adaptable to datasets with higher variability or complex fluctuations. Although it has limitations, exponential model give the best balance of accuracy, simplicity, and interpretability for forecasting unemployment trends in Malaysia. While the polynomial model fits historical data better, its complexity and overfitting risk make it less reliable for long-term predictions. Therefore, the exponential model is ideal for capturing the general upward trend of unemployment, making it a practical choice for predictions.
So, for the conclusion of our study is the exponential model with the lowest sum of square error SSE of 51,488.9 was the most accurate and effective at capturing the overall upward trend in unemployment. The linear model was simple, and the polynomial model captured fluctuations, which both have limitations in predictive reliability. The exponential model balances accuracy and simplicity making it the most suitable for forecasting. However, it shows limitations in handling anomalies or sudden economic shifts. Fourth, so future work should explore advanced techniques such as machine learning and include additional socio-economic variables like GDP and inflation to improve accuracy. Regular updates to the model will ensure continued relevance and provide deeper insight to support policymaking and economic planning in Malaysia. So I think that's all from our group. Thank you.